So now that we know something about truth functions and how they work, we can use these in order to determine the truth table for various statements as well as arguments, okay? And this will be very useful because it'll help us identify properties of statements as well as help determine the validity of statements. So how do you create a truth table? So the first step of creating a truth table for a statement is to make sure you have translated the statement into the language of propositional logic. And we've learned how to do this in lesson 5, part 1. Second, you write down the statement in propositional logic, okay? Third, you create columns for each logical operator and variable. Fourth, you figure out how many rows you will need. The formula for determining the number of rows is L equals 2 to the power of n, where n equals the number of distinct variables. So here you have L, meaning the number of lines, equals 2 to the n power, where n equals the number of distinct variables, okay? So if you have, let's say, 2 distinct variables, then the number of lines you'll have is 2 to the second power, okay, which is basically 2 times 2, so you'll have 4 lines, okay? If you have 3 distinct variables, okay, then you will have 2 to the third power of lines, which is 2 times 2 times 2, okay? So that will be 8 lines. So if you have 3 distinct variables, you have 2 to the third power of lines, which is 2 times 2 times 2, which is 8. Okay, and that gives you 8 lines for 3 distinct variables, okay? Then you add the number of rows to your columns, so you now have a table with columns and rows. And then you determine the initial truth values for each distinct variable and place these truth values in the appropriate cells. The same method will always be used for any statement or argument in the beginning, okay, when you initially determine the truth values for distinct variables. Then finally, you determine the truth values for the logical operators by using the truth value for the appropriate distinct variables and the truth function for the appropriate logical operator. Okay, so I'm going to illustrate these steps a little bit more with examples, okay? So here we have a statement in ordinary language, and we're going to go through the process of going from this statement to a truth table for this statement, okay? So the statement is, if the moon is made of cheese and Las Vegas is in Nevada, then either Jennifer Aniston is famous or the moon is not made of cheese. Now what we're going to do is identify all the simple statements that make up the statement. And the first simple statement we have is the moon is made of cheese. And we're going to give this statement the propositional variable m, okay? Our next simple statement is Las Vegas is in Nevada, and we're going to give that statement the propositional variable L, okay? And then we have the simple statement Jennifer Aniston is famous, and we're going to give that simple statement the propositional variable J, okay? And if you look here, we have the simple statement the moon is made of cheese, okay? So the moon is not made of cheese is actually a compound statement, and that compound statement is made up of the logical operator represented by the not and the simple statement the moon is made of cheese, okay? So the simple statement here is the moon is made of cheese, and we've actually already given a propositional variable to that statement. We've done it here. So the moon is made of cheese was given the propositional variable m, so we're going to use that same propositional variable for the same statement here because it occurs in the same passage, okay? So we're going to give m to this simple statement, the moon is made of cheese, okay? Now after we identify the simple statements, we want to go ahead and identify the logical operators. So notice that here we have if, and we also have then here, okay? And if and then are used together to indicate one logical operator, which is the horseshoe conditional, okay? And that horseshoe conditional will go where the then is. So we're going to put the horseshoe conditional right there, okay? We also have here the word and, okay? And indicates the conjunction dot, okay? So we're going to replace this and with the conjunction dot, okay? Then we have here the disjunction or, and or indicates that we're going to use the disjunction wedge, okay? So we're going to replace that or with the disjunction wedge. And then finally we have here the negation not, and we're going to replace this negation not with the tilde. Okay? So now that we've gone ahead and identified all the logical operators and the simple statements, we're going to write this out. Okay? So we have here M dot L horseshoe J wedge tilde and then M. Okay? Now if you look here, this is not a well-formed formula. We have a lot of ambiguity here. So what we need to do now is make sure to add in the parentheses where they are appropriate that bind the little component parts that make up this larger complex compound statement. Okay? When we look here to the statement, we can see that the if, which begins the conditional statement, is here. And so everything that comes after the if, which is here to here, before the then, makes up the antecedent of the conditional statement. Okay? So here's where that conditional horseshoe went. So that tells us that these two components here, the M and the L, go together with the conjunction dot to make up one unit. Okay? Then we notice here that we have, after the then, okay, an either, okay? And whatever comes after the then, including the either, okay, makes up, and this, whatever comes after the then goes all the way up to here, okay, makes up the entire consequent of the conditional statement, okay? So then we know that everything after the then, okay, including the either, okay, and ending after the M, will make up the second component of this larger complex compound statement. Okay, so here now we have a well-formed formula. Okay, we have a statement that is grammatically correct in propositional logic. Notice how here we have in this part of the larger conditional statement the conjunction M dot L. And then here, in this part, the other half of the larger conditional statement, we have J wedge not M. Okay? Now we can also identify the main operator. Okay? And the main operator, remember, is the logical operator that connects the two largest components that make up that compound statement. Or, if it's a negation, it's the negation that's outside, that ranges over the largest component of the statement. Here, the negation is inside the parentheses, so remember, whatever is inside a parentheses cannot be a main operator. And instead, we have the conditional horseshoe that's bringing together the two largest components. So here's one, and here's another one, okay, in order to make up the statement that is the complex compound statement, okay? Okay. So now that we've done this, let's go ahead and create a truth table for this statement. Okay, so in order to create the truth table for this statement, the first thing that we want to do is go ahead and write the statement down. Okay, so we're going to write that statement down, and we're going to give next each of the variables as well as each logical operator their own column. Okay, so we're going to go ahead and give them each their own column. Then we have to figure out how many lines we need. Okay, so remember, the formula for how many lines we need is the number of lines equals 2 to the n power, okay, where n equals the number of distinct variables. Notice how here we have 1, 2, 3 distinct variables, okay? This is not a distinct variable because n occurs here as well. So we only have 1, 2, 3 distinct variables, okay? So n equals 3 then. Okay, n equals 3 distinct variables, which means the number of lines will be 2 to the third power. Okay, and 2 to the third power is 2 times 2 times 2. Okay, so 2 to any power is basically 2 times itself that many times. Okay, so 2 to the third power is 2 times 2 times 2, and this equals 8. Okay, so we are going to have a total of 8 rows. Okay, so we have 8 rows, and we're going to go ahead and fill them in. Okay, So now you see that we have a chart here, okay, or a table. Now, given that we have a table, we want to start with the initial distribution of truth values to each distinct variable, okay? And the way that we do so will always be the same regardless of whether or not we have an argument or a statement, and regardless of what kind of argument or statement we have, as long as it's in propositional logic, okay? So the way that we initially distribute the truth values for the distinct variables will be as follows, okay? The first thing that you want to do is when you come to your first distinct variable, okay? So M is our first distinct variable, reading from left to right, okay? So when you come to your first distinct variable, you want to go ahead and take the number of lines that you have. Doesn't matter how many number of lines that you have. If you have 4, if you have 2, if you have 8, if you have 16, doesn't matter, okay? You take, regardless of how many number you have, you take the number of lines you have and you divide it in half, okay? Then after you divide the lines in half, okay, so you have 4 and 4, what you want to do is give the first half all true and the second half all false. So this is what you'll have, okay? So you have all true for the first half and all false for the second half, okay? Then when you come to the next distinct variable, you want to cut the halves in half, okay? So you're going to end up with quarters. So you cut the halves in half, okay? And now we have quarters, okay? And what you do is you alternate for each quarter, starting with true for the first quarter, false for the second quarter, true for the third quarter, and false for the fourth quarter, okay? So you alternate true, false for each quarter, okay? Then when you come to the next distinct variable, in this case we have J, okay? You want to now cut the quarters in half, okay? So we cut the quarters in half now. Okay, so now we have eighths, okay? And you want to alternate for each eighth, okay? True, false, true, false, true, false. So here we have true, false, true, false, true, false, true, false, okay? Now, notice how J was our last distinct variable, okay? Because M actually occurs here again. Now, the way to know that you've actually distributed initially these truth values correctly to the variables given is that on the last distinct variable you have, you're alternating in every row true, false, true, false, true, false, okay? So if you come to the last distinct variable you have and you're not alternating in every row true, false, true, false, true, false, then you've done something wrong, okay? So now with this variable here, which is not a distinct variable, what we want to do is go ahead and use the same truth values that we initially gave the variable when we first came to it, okay? So we gave this variable M all true for the first half and then all false for the second half. So we're going to go ahead and repeat the same thing here for the M here, okay? So we have all true in the first half, all false for the second half. Okay, so this is what you do for the initial setup for any truth table for any statement, okay? You do the same process. You write down the statement, you set up the columns, then you distribute the truth values for the distinct variables, okay? And then for any repeated variable, you simply take the truth values that you've given to the same variable initially and go ahead and give them to the repeated variable, okay? Now, at this point, what we want to do is determine the truth values for all the columns for the logical operators. Now, here's something that you have to understand. When you're determining the truth values for all the columns for the logical operators, what you're doing is you're actually determining the truth values for each of the compound statements that make up the larger statement. Okay, so when you're putting a truth value in a column for a specific logical operator, For example, here, when you put a truth value here in this cell, okay, what you're actually doing is determining the truth value for the statement that this conjunction dot is actually creating, okay, by pulling together this statement M and this statement L, okay? The first thing you want to do is identify the main operator of the statement that you're doing a truth table for. Then the column underneath that main operator will be the last column that you actually put truth values in, okay? And the reason for that is because truth values in propositional logic are compositional. So the truth value of this last main operator depends on the truth value of its component parts. And its component parts depends on the truth value of its component parts, okay? So the order in which you have to do these truth values for the logical operators is to start with the smallest units, okay, inside parentheses, okay, and then move your way outside of the parentheses, okay? So let me illustrate. Now, notice how, because we've identified the main operator here, okay, we actually have two components that make up this larger statement. Here's one, okay, surrounded by the parentheses here, M dot L, okay, and here's another one surrounded by the parentheses here, J wedge tilde M, okay? Now, because there are two component parts, okay, we need to make sure to do one first, then the other, and then do the main operator, okay? It doesn't actually matter which side you choose to fill in first, if you work with this side or if you work with this side. However, you must do both sides first and then do the main operator, okay? So we're going to start over here. Okay, so in order to determine the truth values for this tilde here, this negation sign, which is actually determining the truth value for the statement, not M, okay, we want to use this column here, the truth values in this column, along with the truth function for the tilde, okay? Remember, the truth function for the tilde is if some statement P, and P could be any statement, is true, then tilde P is false. And if some statement P, any statement P, okay, is false, then tilde P is true, okay? So we're going to go ahead and use the truth values for this column here for the M to determine the truth values for not M, and we're going to put those truth values here underneath the tilde, okay? So if M is true, then tilde M is going to be false, okay? And if M is true again, then tilde M will be false, okay? And if M is true again, then tilde M will be false, okay? And again, if M is true, then tilde M will be false, okay? And if M is false, then tilde M will be true, okay? And this will be the same for all of these three, right? So if M is false, okay, then tilde M will be true. Okay? So these are the truth values that we will have for this column, okay? They're exactly the same as the ones that I've written down. It's just that now you can, you know, see them a little bit better because they're typed, okay? So now we want to determine the truth value for this column here. Okay, so in order to determine the truth value for this column here, we're going to use the truth value for its component parts, okay? And so parts that make up this statement here is the statement J, so we're going to use the truth values for J, okay? And the statement not M, okay? So because the other part of this disjunction is not M rather than just M, we're going to use the truth values for the statement not M, which is underneath the negation sign. So these are the two columns that we will be using, okay? Now, remember, we're also going to be using not only the truth values here in these columns, but the definition of the logical operator, which is the truth function for the logical operator that is the wedge. The one rule that defines the truth function for the logical operator of the wedge is that a disjunction is false only when both of its parts are false, okay? In every other case, it's true. So, if we look here, if if J, which is half of the disjunction, is true, and not M, which is the other half of the disjunction, is false, then given the truth function of the wedge, the statement J wedge not M will be true. Okay? Because remember, again, the truth function for the wedge is that the disjunction is only false when both of the parts are false. So if one is true and the other is false, then the disjunction is still going to be true. Okay? So here in this column here, we have the J being false and the not M being false. So in this case, we will have a disjunction, which is false. And we'll put that right underneath the wedge. Okay? So here again, we have J being true and not M being false. So the statement J wedge not M will be true. Okay? And here we have J being false and not M being false. So the statement J wedge not M will be false. Okay? And then here we have J being true, not M being true. So the statement J wedge not M will be true. Okay? And here we have J being false, not M being true. So the statement J wedge not M will be true. Okay? And here we have J being true, not M being true. So the statement J wedge not M will be true. And then finally we have J being false and not M being true. So we have J wedge not M being true. Okay? So once again, in order to determine the truth value for the wedge here, which is actually for the statement J wedge not M, okay, we use the truth value of its component parts, which is the truth values for J and the truth value for not M, okay, along with the truth function of the logical operator that is the wedge. Okay? And here it is typed. So that's the exact same thing that we've written down, but now it's typed. Okay? Next, what we want to do is move on to this side of the conditional statement, which is our main operator, right? So this is our main operator, which tells us this entire statement here is actually a conditional statement. And remember, we want to wait until we do both sides, okay, before we do the truth values for the conditional statement, okay? So here, inside these parentheses, we have the conjunction of M and L, okay? So this inside the parentheses is a compound statement that is a conjunction, okay? So like we did over here, in order to determine the truth value for the conjunction now, we want to use the truth values for its component parts along with the truth function of the logical operator that is the dot, okay? So we're going to use now the truth values for the M, which is one part of the conjunction, and then the truth values for the L, which is the other part of the conjunction, okay? And then we're going to use the truth function for the dot operator. Remember, the truth function for the dot operator, the one rule that defines it, is that the conjunction is only true when both of its parts are true. Okay, so the only time that this statement will be true is if M is true and L is also true. If you don't have that condition being met, then it's going to be false. So here you have M being true and L being true, so the conjunction of M dot L will be true. Okay, and again you have M being true and L being true, so the conjunction of M dot L will be true. Now here you have M being true, but L being false. So the conjunction of M dot L will be false. And again, here you have M being true and L being false. So the conjunction of M dot L will be false. And then here you have M being false and L being true. So the conjunction of M dot L will be false. And you have here again M being false and L being true. So the conjunction of M dot L will be false again. Okay? And notice how in these two lines here, you have M being false, okay, and L being false as well. So in both these, you'll have the conjunction of M dot L being false. Okay, So now what we've done is determine the truth values for this part of the conditional, okay? And just to show you a little bit more clearly, this is what you'll have, okay? So this is the same thing we wrote down, it's just now printed, so you can see it a little bit more clearly. Okay, finally, now that we've done the truth values for the parts of the conditional statement, we can address the truth values for the entire conditional statement as a whole, which we'll put under the conditional horseshoe, okay? In order to determine the truth value for the conditional horseshoe, okay, which is the truth value for the entire statement as a whole, what we need to do is, again, use the truth values of its component part and the truth function for the logical operator of the horseshoe this time, okay? So we will be using the truth values for the conjunction here, okay, and the truth values for the disjunction, because those are the main parts that make up the conditional. This conditional statement is a statement that has as its main parts the conjunction and the disjunction. So that's why we're going to use the truth values for this column, the dot, and the truth value for this column, the wedge, in order to determine the truth value for the conditional, okay? And the one rule that defines the truth function for the logical operator, that's the horseshoe, is that a conditional statement is false only when the antecedent is true and the consequent is false, okay? In all other cases, the statement is going to be true. So the antecedent, remember, is the statement that takes this position in a conditional statement in front of the horseshoe, and the consequent is a statement that takes this position here after the horseshoe, okay? So anytime this column has true as this truth value, and this column here has false as its truth value, the conditional statement will be false. And in all other cases, it'll be true. So here you have true, okay? And here you have true. So the conditional statement will be true, okay? And here you have true, and here you have false. So the conditional statement here will be false, okay? Here you have false, and here you have true. So the conditional statement here will be true, okay? Here you have false, here you have false. So the conditional statement here will be true, okay? Here you have false, here you have true. So the conditional statement again will be true, okay? Here you have false, here you have true. So the conditional statement will be true, okay? Here you have false, here you have true. So the conditional statement will be true. And then here you have false, and here you have true, okay? And the conditional statement will be true, okay? So we've determined the truth value for this entire statement here, okay, by using the truth values of its component parts, okay, and building up to determine the truth value for the statement itself, okay? Now here's the thing. These are all truth values for the parts of the conditional statement, okay? But the truth value for this entire statement is in this column here, okay? So these are the truth values for this statement. Now, when I'm talking about truth values for this statement, when we're using a truth table, what we're talking about is all the possible ways that this statement can be either true or false. So these are possibilities, okay, in terms of truth value that this statement can have. So this statement can be true if its component parts have this kind of truth value, or if its component part have this kind of truth value, or if they have these kinds of truth values, okay? However, notice that this statement can also be false only one way, okay? If its component parts have these truth values, okay? So all these truth values here, each line, okay, represents a possible truth value that this statement can have. So once we were able to determine the truth table for a statement in propositional logic, one cool thing that we can do is identify logical properties of that statement, okay? And these logical properties belong to the statement based on the form or the structure of that statement. It doesn't matter what the content of that statement is, it actually depends on the form or the structure of that content. And we can use the truth table to actually determine the logical properties that certain statements will have. So contingent statements are statements that are neither necessarily true nor necessarily false. They are sometimes true and sometimes false, okay? Non-contingent statements are statements such that the truth values in the main operator column do not depend on the truth values of the component parts. The statement is either always true or always false based on the structure of the statement alone, okay? So you can have broadly contingent statements and non-contingent statements, and being contingent or not contingent are logical properties that belong to the statement itself based on the form of that statement, okay? So notice here, this is the example that we worked with just recently, and we have in its truth table, so this is the column that represents the possible truth values for this statement. According to the truth table for this statement can be true and false, okay, depending on the truth values of its component parts, okay? So because it can be true, okay, or false, this is a contingent statement, okay? So the truth value of this statement will depend on the truth value of its component parts, okay? And it's possible for it to be true or, so true, and here's all true, or false, depending on what their component parts are, okay? So now with non-contingent statements, you can have a tautology or a self-contradiction, okay? So tautology is a statement that is necessarily true. What that means is, based on the structure of that statement by itself, regardless of what the content of that statement is, regardless of what the specific propositional variables that that statement has as its truth value, the statement will always be true, okay? So consider this statement here. Apples are red or apples are not red, okay? In propositional logic, this statement is P wedge, not P, okay? So we're going to do a truth table for this. Okay? So like all other truth tables, right, we set it up with writing the statement here across and then determining how many lines we need. The formula, remember, is the number of lines equals 2 to the n power, where n equals the number of distinct variables. So here we have only one distinct variable, okay? So the number of line equals 2 to the n power, okay? Where n equals the number of distinct variables, right? So here we only have one distinct variable, a p, okay? So the number of lines we're going to have is 2 to the first power, which is just 2, okay? So we have 2 lines here, okay? So now that we have the lines and we've set up the columns, okay, we're going to go ahead and initially distribute the truth values for the distinct variables. And remember, the rule for distributing the initial truth values for the distinct variables is first, when you come to the first distinct variable, you cut the number of lines that you have in half, okay? And then you alternate the first half true and the second half false, right? So true and then false, okay? And since that's our only distinct variable, okay, we're done, okay? And notice how, because that's our only distinct variable, we're alternating true, false, okay? And because this here is not a distinct variable, it's the p over here, we're going to use the truth values that we've given here in these columns as well, okay? So this will be true and this will be false, okay? Then we want to determine the truth value for the logical operators, okay? And remember, you want to start with the smallest units first, working your way out. Here we don't have any parentheses, but notice the main operator for this statement here is the disjunction wedge, okay? So this is a disjunction, okay? The disjunction is the disjunction of P, okay, and the statement not P. So P, okay, makes one part of the disjunction, and not P makes the other part of the disjunction, okay? So we do the truth values for the wedge disjunction last, because that's the main operator, and we have to do the truth values for its component parts before we can do the truth values for the wedge. which means we have to do the truth values for this negation before we can do the truth value for this wedge. So we go here to where the negation column is, and we determine the truth value here for this cell for not P, okay, by using the truth values for P along with the truth function of the tilde not P, okay? So again, the truth function for the tilde is that if P is true, then not P is false, okay? And if P is false, then not P is true, okay? So now that we've determined the truth values for the parts of this disjunction, we're going to determine the truth values for the disjunction. And remember, when we do the truth values for the main operator, we want to use the truth values for its parts, right? So like we said, this disjunction is made up of the P, okay, and not P. And the truth values for not P is actually under the tilde, okay? So we're going to use these two columns along with the truth function for the logical operator that is the wedge, okay, to determine the truth values here, okay? So according to the truth functions for the logical operator wedge, if P is true, so if one part of the disjunction is true and the other part of the disjunction is false, okay, the disjunction itself will be true, okay? And then again, if P is false, if one part of the disjunction is false and the other part is true, okay, then the disjunction itself will be true, okay? So, just to give you a clearer idea, okay, here are the truth values written down. So we have true, false, false, true, and then true, true, okay? And this here is the column that represents the truth value for the entire statement that is the disjunction, okay? Now when we look at this truth table for the statement here, okay, notice how the only possible truth value that this statement here can have is true, okay? Because the entire column underneath the main operator for this statement is going to be true. So this statement cannot possibly be false. Remember, each line of this truth table represents a possible truth value that this statement can have. So if each line of this truth table represents a possible truth value that this statement can have, and the truth table gives you all the possible truth values that this statement can have, then this statement cannot be false, okay? The reason why it cannot be false is because of the structure of the statement itself, okay? So we can replace P here and P here with any other statement as long as we do it consistently. So if we put a statement, let's say Y here, and then because this is a P and this is a P, we also put a statement Y here, that statement Y wedge tilde Y will always also be true, okay? It will not be able to be false. This now is called a tautology. It is a statement that is necessarily true, okay? And it's true because of the structure of that statement itself. Now this is a type of non-contingent statement. Another type of non-contingent statement is a self-contradiction, okay? So a self-contradiction is a statement that is necessarily false, okay? So here we have an example of a statement that is a self-contradiction. Apples are red and apples are not red, okay? And this is what the statement looks like in propositional logic. So let's look at the truth table for this statement to see why it's a self-contradiction, why it's necessarily false. So here again, we have the setup for the truth table, and we're going to go ahead and this time I'm just going to put in the truth values, okay? And I'll explain it, but I'm not going to write it in, okay? So we've already determined the lines, and here notice we only have one distinct variable as well, okay? So there's a P and there's a P, so that's only one distinct variable. So for the first distinct variable that we come to, we cut the number of lines in half and we distribute the first half true and the second half false. So this is what we're going to have. And because this is not a distinct variable, we've already given truth values to the letter, okay? We're going to go ahead and use the same truth values where this variable occurs again. Okay, so that's what we have. And now we're going to determine, again, the truth value for the smallest component that makes up this statement, okay? So this statement is a conjunction, and as such, that conjunction dot is the main operator, okay? Which shows you that this is one part that makes up the conjunction, and this is the other part that makes up the conjunction. So we're going to hold off on filling in truth values for this column here under the conjunction dot until the end, okay? So before we can do these truth values, we need to do the truth values for its component parts. We've already done the truth values for the P over here, and now we have to do the truth value for the not P, okay? So again, we're going to use the truth values for this column P here in order to determine the truth values for this column, okay, along with the truth function of the tilde operator, okay? So when we do that, we end up with false true, okay? So whenever P is true, tilde P will be false, and whenever P is false, tilde P will be true, okay? Then finally, we can go ahead and determine the truth value for the statement itself, okay, this entire statement, which is a conjunction, and we put those truth values right underneath that logical operator that is the main operator, okay? And we will use the truth values for its component parts, right, which was P and the tilde P, okay, because this half of the conjunction is not P, this half of the conjunction is tilde P. So we're going to use a truth value that goes under the tilde, because the truth value that goes under the tilde are the truth values for tilde P, okay? So we're going to use this P being true and not P being false gives us, according to the truth function of the conjunction dot, a false statement, okay? And when P is false and negation P is true, we also have a false statement, okay, according to the conjunction dot operator, okay? Now when you look at this truth table for this statement, okay, notice how all the truth values that are possible for this statement here is false, okay? So this statement can only be false. There's no possible way that this statement can be true, okay? Why? Because the truth table shows you all the possible truth values that this statement can have. So if it shows you all the possible truth values that this statement can have, and this statement can only have false as its truth values, then this statement cannot be true, okay? So this is a necessarily false statement. It is a self-contradiction, okay? The self-contradiction also, just to note, is because of the form or the structure of this statement. Has nothing to do with the content. It has nothing to do with what the P would be in terms of what kind of statement it would be, okay? You can put any kind of statement in here. You can put the statement apples are red in here, or you can put the statement birds fly, or you can put the statement cake is delicious, okay? It doesn't matter what kind of statement you use to replace this P, okay, as long as you also use that same statement to replace the P here, okay? You'll always end up with a necessarily false statement, a statement that cannot possibly be true, okay?